Okay, hello North Tahoe High physics students. Today in this hopefully what will be a brief video, we're going to discuss the conservation of energy. We've got three objectives. One is to recognize the forms of energy that make up something called mechanical energy. Two is to understand what it means for energy to be conserved. And three is to be able to solve conservation of energy problems. No one gets through a first-year physics course without having to solve a lot of conservation of energy problems. It's a big, important idea, and we're going to practice it a lot. So conservation of energy is an important aspect. What does it mean for energy to be not or conserved? It means that it's not going to be created or destroyed. And an example would be this little brat right on a hill. And I call him a little brat because after 4 years of drought, he's got all this snow to play with and he's so happy on it. But imagine what we're dealing with. At the very top of the hill, he's got what we typically call gravitational potential energy. And of course, as he gets lower on the hill, in this case, he starts going faster and faster. So he develops more and more kinetic energy. So all we're saying in terms of conservation of energy is that one form of energy can be transformed into the other, but the total amount of energy cannot change. And we're going to take a look a little bit more specifically about what that means. Also, work is part of it. How did this kid get this potential energy in the first place? He had to do work, or probably his parents did work, pulling him up to the top of the hill. They had to exert a force, and they had to exert that force over a distance of the hill, force and distance, to give them this potential energy to begin with. But once we've given the system, and the kid and the sled is the system, that potential energy, the energy has to stay the same. So we can transform it into potential or kinetic. So let's quickly review then the main types of energy that we're going to deal with, and what is this thing called mechanical energy. One of the energies that we've dealt with already in some detail is kinetic energy, and we saw that in order to change something's kinetic energy, you have to do work on it. We call that the work energy theorem. So kinetic energy, if you remember, which we'll just call Ke, was given by the equation 1/2 mass times velocity squared. I want to pause and look at those units just for a moment, right? Mass has units of kilograms, and velocity is meters per second, but we're squaring it. So that's meters squared per second squared. That is something that we know better than as actually a Newton meter. And we also call a Newton meter a joule. Right, so let's look at the other forms of energy which we have not explored mathematically yet. And if it's an energy, they should have the same units, right? Okay, so let's look at the other one, gravitational potential energy. We've talked a little bit about it, but we haven't looked at it in much detail mathematically. Remember, we should see a connection between work, force times distance, and the energy itself. So we call gravitational potential energy, our book uses U for potential energy, sub G for gravitation. And let's just think about what happens. In this simple graphic, we have a book low down, starting maybe on the earth itself, on the floor, and we're going to lift it up and give it gravitational potential energy. How is that done? Well, we have to lift. That means we have to exert a force. And usually the force that we have to lift with, if we're going to do it at constant speed, would be the weight of the book. If the book weighs 10 newtons, to push it upwards, I have to exert 10 newtons of force. Weight, we know from our force unit, is mg, mass times the acceleration of gravity. So we're going to exert that weight or that force upwards, and of course we have to do it some distance upwards. So that's my displacement vector. Usually, sometimes we use delta y or we use distance, but since we're talking about lifting upwards, we kind of specifically often use the variable h for height. So again, this is our new equation for gravitational potential energy. Mass times the acceleration due to gravity times height. Let's look at the units again real quick. Mass, of course, is always going to be in kilograms. We know the units of acceleration are meters per second squared. And the units of h would be in meters. So we put all of that together and we get kilogram meter squared per second squared, which is a Newton meter, which is a joule. So we're pretty confident. Oops, my pen's freaking out here. we're pretty confident that this is in fact an energy. It has the same unit. Okay, and the last form of energy that's going to make up mechanical energy is another form of potential energy. That means it's energy that can be stored, and it's usually called spring energy. And I believe our book uses the variable U for potential and S for spring. The equation, and we'll talk a little bit more about it in detail later, is 1/2 K x squared. K is what's called the spring constant. And it's kind of a ranking of how stiff the spring is. How easy is it to compress, or how easy is it to stretch? If a spring is really stiff, it's hard to stretch or it's hard to compress. It has a high spring constant. If a spring is kind of loose and easy to stretch or compress, it has a low spring constant. The units for spring constant K are newtons, the force required to stretch it or compress it, per meter. So the spring constant units would be newtons per meter. X here is the distance that it is stretched or compressed. So this graphic shows us actually doing work, right? We're going to exert a force, and we're going to exert a force over some distance compressing it. So that's the compression, and you could also do a stretching distance from equilibrium. So X has units, again, of meters. So we put these things together then in terms of the units, right? K is a Newton meter, and times x squared, which is meters squared. So let's break that Newton into what it is. A Newton is a mass and an acceleration times acceleration. So the mass is kilograms, the acceleration is meters per second squared. Let's look at these meters. This meter would cancel one of those, so I have an extra meter there. So it's kilogram meter squared per second squared, which again is a Newton meter or a joule. So all of these are forms of energy. It's really important to sort of see the connection between work. If we want to change something's kinetic energy, we exert a force over a distance. If we want to store energy, we exert a force over a distance. If we want to store energy here, we push or we stretch with force over a distance. So all of these are related to work as well. So what is mechanical energy? Mechanical energy is simply the sum of kinetic and potential energies. So I would define this thing, maybe I'll call it ME for mechanical energy, as simply the kinetic energy an object or a system has, plus its gravitational potential that a system has, plus its elastic or its spring potential energy that a system has. Mathematically then, I'm just going to replace these with their equations. That would be 1/2 mv squared plus mgh for gravitational potential plus 1/2 kx squared for spring potential energy. That's mechanical energy, simply the sum, kinetic, and plus the two potentials. Okay, so before we begin solving problems, let's think a little bit about what does it mean for mechanical energy to be conserved. We've seen conserved things before in science. Before this unit, we dealt with the conservation of momentum. That meant the momentum of a system before an interaction had to be the same as the momentum of the system after. Momentum wasn't created or destroyed. In chemistry, we deal a lot with the conservation of mass. The mass has to, before a chemical reaction, has to be the same afterwards. For physics, mechanical energy means the same thing. Mechanical energy is never created or destroyed. And what that means is the energy may change form, but the total amount of energy in a system must remain the same. So before we solve an example problem here, let's take a look then mathematically at what that's going to mean. We're going to have then sort of initial conditions, which I'll call I, and then final conditions, just like we do with all conservation of momentum, and all of these energies have to sum the same before and after. So kinetic energy initial plus gravitational potential initial plus the spring potential initial has to equal the kinetic energy final plus the gravitational potential final plus the spring potential final. So let's go ahead then and try to solve this problem. This problem is out of our book. in chapter 10. So it says a 1,500 kilogram car is approaching a hill as shown in the figure at 10 meters per second. When it suddenly runs out of gas, we'll break it down. A, can the car make it to the top of the hill by coasting? And B, if your answer to part A is yes, what is the car's speed after coasting down the other side? Okay, so let's take a look at this problem then. We'll break it into two steps. The first car, can we make it to the top of the hill? So let's just think about where our initial and final conditions exist. Initially, we're concerned with that region right there. And then finally, we're concerned about the top of the hill. So let's think about our energies then that we have to deal with. Initial conditions, we do have kinetic energy, right? This could be a little confusing at first. We have some potential energy, but really what all that matters are changes or differences in potential energy. So I'm going to define for this problem that potential energy at this point is 0, and up here there is some amount of increase in potential energy. So even though I can talk about potential energy before, I'm going to set it up this way. UG final. So let's say that this is 0, and we're starting off with kinetic energy, and if we're just going to make it to the top of the hill, we're going to imagine we're going to stop at the top of the hill. So the top, we would have no kinetic energy for this problem. So essentially we're asking, do we have enough kinetic energy to be transformed into the right amount of potential energy at the top? So let's go ahead and figure out. We need the kinetic energy to begin with, which is 1/2 mv squared. So it's going to be 1/2. The car is 1,500 kilograms, and we're taking 10 meters per second and squaring it. If my math is right, that's about 75,000 joules of energy it has as kinetic. What does it need afterwards? It's going to have its potential energy increased by some amount. So let's figure out how much is that potential energy increased by. Well, UG is mgh, and the mass of the car is 1,500 kilograms. We'll use G as 10 meters per second squared, and H is 5 meters higher. So we're going to increase its potential energy by going 5 meters higher. And if we do that problem, 1,500 times 50 gives us 75,000 joules. So the answer to this question is yes, we do have enough energy to take this kinetic energy and transform it to potential energy at the top. It's exactly the same amount of energy. Let's take a look at part B then. How fast will it go at the bottom here if it gets over the top, just gets over the top, and transforms its potential energy into kinetic down here? All right, so again, we have to define our starting and our final points, our initial and final. So we're going to imagine for the part B, the car is at the top of the hill. It's not moving, or it's moving so slow that its kinetic energy is negligible. So all it has is potential energy. And at the bottom of the hill, we're kind of calling that ground zero. So it no longer has potential energy, and at the bottom of the hill, it possesses only kinetic energy. It's moving. So let's take a look mathematically at what that means. It means that our mechanical energy here, if we have no kinetic energy at the top, the KE term drops out on the initial side. If we have no potential energy at the bottom, the UG drops out on the final side. So our conservation equation looks like this. Potential is transformed into kinetic. So one thing you'll see about problems like this is the mass doesn't actually matter. The mass will cancel out. And if I do a little bit of algebra and solve for V, right, because that's what we want, the car's speed after coasting down, I'm going to get something that looks like this. 2gh, the square root of that. And the h is a change in potential, or a change in height in that case. So I'll go ahead and solve this. And I get the square root of 2, g is 10 meters per second squared, and the height drop was 10 meters total. So that's what I put in there. And that's the square root of 200, which is about 14.1 meters per second. Real common problem. What is the velocity after changing your energy from potential into kinetic? We'll see lots of those. Let's set one more up, and then we'll call it a day for this lesson, and you'll practice on your own. Okay, so this problem is one of the stranger problems that you see. I think the reason they put it in here is it encompasses all three forms of energy that make up mechanical energy. Let me read it to you and then set it up. I'm going to let you work on the mathematics of it, though. It says, a new event in the Winter Olympics has been proposed. An athlete will start with a 100 will sprint 100 meters starting from rest, then leap onto a 20-kilogram bobsled. The person in the bobsled will slide down a 50-meter long ice-covered ramp, sloped at 20 degrees, into a spring, carefully calibrated spring constant of 2,000 newtons per meter. The athlete that compresses the spring the most wins. Lisa, whose mass is 40 kilograms, has been training for this event. She can reach a maximum speed of 12 meters per second in the 100-meter dash. How far will Lisa compress the spring? And B, the Olympic Committee has exact specifications about the shape and angle of the ramp. Is this necessary? If the Olympic Committee asks your opinion, what factors about the ramp will you tell them are important? So let's go ahead and just think about the problem in terms of energy for part A. How far will Lisa compress the spring? So we have to think about the energies involved before and after. So let's look at the problem. She's running on top of a hill. So when she hits the sled, she has kinetic energy. She's also some distance or some height above the spring. So she also then has potential energy. You can imagine she's going to go down the hill, and she's going to compress this spring some amount. When she compresses the spring, she'll be stopped, so she won't have kinetic energy. She's also really, really low on our reference scale here, so she'll have no potential gravitational energy. But she will have transferred this energy into spring energy. So let's set up the conservation problem. So what we just said is this problem starts out with only kinetic energy and gravitational potential energy. There is no spring energy at this point. At the very bottom of the slope, she stopped after she compressed the spring, so no kinetic energy. She's also as low on our reference scale as we can imagine, so she has no gravitational potential energy. So mathematically, it'll look like this. Her kinetic energy, 1/2 mv squared, plus her gravitational potential energy, mgh, will equal her spring energy at the end, 1/2 kx squared. So a couple things you got to figure out. You got to figure out what is her kinetic energy to begin with, and then how high is she, right? And that's why this problem states in that situation 20 degrees, and then solve this mathematically. We'll work the solution out together in class, but give it a shot first.